Hi, my name is Bryant and I am a development engineer for Texas Multicore Technologies. This video is the first of a three-part tutorial series. In this video, I will be giving a high-level overview and background of Sequencel. To get started, we'll look at a quote by Dr. Edsger Dijkstra. In his 1975 essay titled, "How Do We Tell the Truths That Might Hurt?" Dijkstra said, "The tools we use have a profound and devious influence on our thinking habits and therefore our thinking abilities. The old saying goes that if the only tool we ever have is a hammer, everything starts to look like a nail. Having the right tools for the job is very important. What we'll see in this video is that Sequencel is the right tool for multicore development, solving the multicore programming problem. So first, we'll take a look at exactly what this multicore programming problem is. For this, we'll turn to an analogy. Let's say that there's a contractor that moves boulders. He rents a crane each job and it's working great. One day, the crane rental guy delivers two smaller cranes, saying that together they can lift more than the big one. But now the contractor must split the boulder in two. This is analogous to the advent of dual-core processors. Developers could no longer just write code. If they wanted to make full use of their processors, they had to handwrite parallel code. Next, the crane rental guy brings four smaller cranes, again saying that together they can lift more than the previous two cranes. But now, the contractor must split the boulder into even more pieces. When quad-core processors came out, developers then had to parallelize their code even more to again make full use of their processors. Next, it's 8 cranes, and splitting the boulder into 8 pieces. The contractor begins to wonder if he's in the boulder moving or the boulder splitting business. We see this now in the software industry. It has become a task in and of itself to parallelize software for large-scale multi-core processing. But why is this a problem? We can use Amdahl's law to see that if a developer is able to fully parallelize 50% of their code, it will at most ever be able to run twice as fast. This also tells us that at 50% parallelization, the code can make full use of at most 2 cores. If a developer is able to fully parallelize 90% of their code, then it will at most ever be able to run 10 times as fast, or make full use of at most 10 cores. In order to be able to take full advantage of an arbitrary number of cores, near 100% parallelization is required. Sequencel is currently the only way to automatically generate near 100% parallelisms. To finish off the analogy, we like to think of Sequencel as Marvin the Martian's ray gun. It takes the boulder and blasts it into a pile of sand. The auto-parallelizing compiler is able to extract the natural parallelisms inherent in the developer's code, and the Sequencel runtime handles executing those parallelisms on any number of cores. Now that we've framed the multi-core programming problem, we'll take a high-level look at what Sequencel is. Sequencel is a functional, high-abstraction, automatically parallelizing language and toolset. We will be breaking each of these aspects down and describing what they mean. Sequencel is a functional programming language. The programming languages most people are familiar with are imperative languages. These are languages like C++, Java, C#, or PHP. In an imperative language, developers specify a sequence of commands for the computer to carry out in order to solve a problem. It is the developer's job to tell the computer how to solve the problem. On the other hand, you have declarative languages. In a declarative language, the developer describes the desired output in terms of the input. It is the developer's job to tell the computer what the solution is, and the computer determines how to compute it. Common declarative languages are SQL, regular expressions, and Prolog. Functional languages are a subclass of declarative languages. A functional language is a declarative language in which the primary operation is function application. There is generally no reassignment or mutability in functional languages. Some examples of functional languages are Haskell, Lisp, and F#. Though Sequencel is a functional language, we often refer to it as a purely functional language. This is because many languages which are called functional aren't actually declarative. Haskell, for example, has ways of specifying execution order, which means that it is not in fact declarative, while Sequencel is. Sequencel is a high abstraction language. Throughout history, humans have dealt with complexity through abstraction. This is readily apparent in the software development field. We've moved from physically wiring machines to writing programs in machine code then assembly language, and then the compiler. Sequencell is another level of abstraction, removing the need for the developer to worry about how to parallelize their code for a given computer architecture. The advent of the Fortran compiler was met with resistance by some developers, as they were able to write assembly code that could outperform the generated assembly code produced by the compiler. Abstraction usually comes with this inevitable cost of performance, but not with Sequencell. In fact, programs written in Sequencell often outperform handwritten parallel solutions on multi-core systems. Sequencell is an automatically parallelizing language. Programs written in Sequencell are written at a very high level without regard to execution order, deadlocks, race conditions, or anything else that usually plagues multi-core developers. These programs are then compiled into highly optimized parallel C++ and optionally OpenCL. These programs do not need to be rewritten or even recompiled to exploit new hardware platforms. The number of cores can actually be changed at runtime. So where does Sequencell fit in? Sequencell programs are written using one of the IDE plugins and tested using the Sequencell interpreter and debugger. Then these Sequencell programs are compiled into parallel C++ code. Why output C++ instead of a binary executable? Sequencell was originally designed to be a self-verifying specification language. In fact, the designers of Sequencell did so in the pursuit of utmost simplicity. The first thing to be trimmed from Sequencell was I/O. So Sequencell relies on the target language to implement the input and output necessary for a complete program instead of reinventing I/O. The choice to output to C++ has also had some far-reaching effects. For example, this allows existing systems to easily benefit from Sequencell through replacing bottlenecks by either directly calling the compiled C++ functions or by creating a C++ DLL and calling that. In the end, Sequencell allows programmers to focus on problem solving instead of parallelizing their solution. It allows them to not miss the forest for the trees, as the saying goes. Because of this, development in Sequencell tends to have a faster time to market. Also, due to the nature of Sequencell's origins, the code quality and readability is greatly improved when using Sequencell. And in addition to all of this, Sequencell allows developers to quickly and easily take full advantage of multi-core systems. In the next video, I will cover the syntax and informal semantics of Sequencell, and dive deeper into how to use the language. Thank you for taking the time to watch this video. If you have any questions or comments, feel free to comment on this video or contact us via our website, which is linked to in the video description. If you're interested in learning more about Sequencell, be sure to subscribe to this channel.